Hello and welcome to part 2 of this UV episode in which we will now cover texel density. So let's jump straight into it. Texel stands for texture element or texture pixel. The two tend to get used interchangeably. I've seen it more as texture element a lot of the time. So the word is basically texture element density or texture pixel density. The texel density of an object is how many texture pixels cover a 1 meter space of a model surface, which is known as pixels per meter or px/m. It can be centimeters, I believe it can also be inches, but typically it is meters that, well, I work with. Now, texture pixels might sound confusing, as I thought it did when I first heard about it. All it means is pixels of the texture, and that does sound like I just moved the words around, but it is just that. It is the pixels of the texture. To follow along in this video, what you'll have to do is go to Edit, Preferences, go to the add-ons and type in Texel, and then select the Texel Density Checker, as this is what we'll be using in the video. Well, I hope you are ready because this is going to get very confusing very fast. To begin, I'm going to give you both formulas. They are going to look confusing to begin with, but hopefully as time goes on it will help you understand quicker, as opposed to me telling you what values things are, then giving you the formulas and then hoping it makes sense at that point. So either way, we're going to start with calculating texel density. So texel density, or TD, is equal to texels across, or TA, divided by real length, or RL, and that is your meters, centimeters, inches and feet. So to calculate texels across, so texels across, or TA, is equal to the UV width, which can only be between 0 and 1, times texture resolution, or TR, and that is your 1024, 2048 and 4096. So let's start off with trying to make things as simple as possible. So if we delete this and we go to our viewer node, and then what we're going to do is we're going to import a plane. The plane specifically needs to be 1 meter. So if we apply the scale and then bring in a new material, and then we're going to call this image texture, or we're going to call this material our texel density checker. Plug it in and then make a new one, and we're going to call this texel density 1024. And then what we're going to do, just so we can see something, is we're going to put on the UV grid like so. So if we were to use this formula, we can see that the UV, if we look at our tensor density checker, we can see that our UV takes up the entire space. And if we use this tensor density checker here, before we actually click calculate, we should be able to do it ourselves. So our texels across is the UV width, so it's 1, it is all of 1, and then we times it by our texture resolution, which is 1024. So 1024 times 1 is 1024. So now we want to calculate our texel density. So we know that our texels across is 1024, and we know our real length is 1. So 1024 divided by 1 is still 1024. So our texel density should equal 1024 pixels per meter. So if we go to calculate TD, we'll see that it's 1024 pixels per meter. So interestingly, if we turn this up to 2 meters and apply our scale there, we should basically just get the idea that it is still, texels across is still the same, but the real length is now 2. So it's 1024 divided by 2, and that equals 512. So if we calculate TD now, we'll see it's 512. The inverse can also be done. So if our plane is 1 meter, but we make our island half, even though it sits in a quarter, we can still work this out. So it's 0.5, so it's 0.5 of our UV width, and our texture resolution is 1024, so that's basically half, so it's 512. Then our density is 512 divided by 1, which again is 512, and that is why if we calculate TD, we can see, yep, the UV space is 25%, but the density is still 512. So one of the texel density calculation gotchas is one that you might not expect. So if we bring in our plane again and make it 1 meter, and then we apply the scale, keep the texel density checker on, and we cut the object in half, for example, or at least this face in half, and then we remove it, you might think that it's going to be 512 pixels, but it's going to be 1024. And that's because we are still using one of the UV grid. So it's not 0.5, it's still one of the UV grid, and then we've also still got the full 1024 pixels. And basically that's because even though the face is cut in half, it's still being mapped at 1024 pixels per meter on the object that it's attached to. So even though we use half the number of total pixels, the size is still the same. So in a nutshell, texel density is pixels per 3D space meterage. Scaled up objects equals smaller pixels per meter, and smaller UV islands equal less pixels per meter. If an item is cut in half, despite it consuming half the amount of total pixels, it still has the same texel density, assuming the UV island and object scale have not changed. So you might be thinking, these are easy to calculate because they're planes, they're triangles, so triangles are just half of what a plane is, for example, when we just saw that it isn't. Basically, it doesn't really matter because obscure shapes work as well. So if we just delete this and bring in a circle, go into edit mode and look at our vertices, and then we checker deselect and scale it in on the X and Y like so, select all, make a face. And then the other thing we need to make sure is that our dimensions are 1 meter, and we apply our scale. And then if we unwrap by projecting from view brackets bounds, this should be 1024 pixels per meter because we're using one of the UV grid and it's a 1024 texture. So if I go over now and select this calculate TD, it will help if we had the face selected, it will say 1024. The only thing that's odd is if we grab this prong, for example, and throw it in the corner, our TD will basically increase or decrease. So if we select this and calculate, we'll see that it's increased past the 1024 threshold, which is odd because our texture is only 1024. There's no 1033 pixels in this for our 1 meter object. So what we can do is, just for reference, if we bring in a plane and we make this 1 meter so it can visualize as our UV grid, and then we select our star, if we were to grab that same point and then literally park it in the corner like so, and then we unwrap the same way again, if we now select this face, it will calculate back to 1024. So won't lie, I have no idea what that necessarily means, but the point that I'm getting at is if it takes up the whole UV grid on either the U or the V, it's more than likely going to be 1024 pixels per meter, unless of course you've got a 2K texture or a 4K texture. If we were to scale this down by 0.5, so now it takes up a quarter of our UV space, it should be 512 pixels per meter, because like we stated earlier, it takes up half of the UV grid, so it's 0.5 times 1024, and then it's 512 pixels per meter, because our real world scale model is 1 meter. So when working with assets in scenes, it is advised to try and maintain a similar texel density across all of your assets. So for example, you might have seen this in the UV video that we did before, where when we had our texel density checker, so this is 1K, and then if we bring this one over, and then we will make this one 4K, for example, so we'll just call this texel density checker 4K, and then we'll make this 4K. Oh, sorry, 4096. The name is going to be 4K texel density checker, like so. And as you can see, we've got a lot more resolution on this. So the texel density will be higher. So for example, if we pull up our 4K and we bring in our plane, say, and then again we're going to make this 1 meter, like so, and what we should get now is it's 4096 pixels per meter. So if we just adjust this, because it's a 496 pixel texture now, and then select the face, we'll see it's 4096. So the key takeaways are that pixels themselves do not equal texel density. Pixels are total pixels in the image. Texel density is the number of those pixels per meter of the object, or pixels equal image budget, and the texel density equals how many of those pixels fall on each meter of your model. When calculating texel density, we can't entirely rely on the U or the V, and this is because when we were working with our planes and our triangles, basically they were what are called axis aligned, as in the vertices are both on the U or the V. So the reason why our star or our jagged shape worked quite well is because even though it wasn't axis aligned, the furthest points were either exactly on the U or exactly on the V. So sometimes we do need to calculate the triangle or the longest diagonal line to basically get a more accurate result, basically. So I'm going to go through both of these right now, and then you can see basically how doing a bit more advanced maths can basically get us a much more accurate result. So to begin, what we're going to do is we're going to grab all of our points and the UV coordinates that they have, and basically this is just going to be quite a bit long because we are grabbing 8 pieces of data. So that's point 1, and then we're going to get point 2, then we're going to get point 3, and then we're going to get point 4. And then what we're going to do is to just neaten it up, we're going to do this, and then what we're going to do is start again. So point 1 on the V, point 2 on the V, and then point 3 on the V, and then lastly point 4 on the V. So these are our points, these are just for reference. So we need our U max distance, and then we need our V max distance. So our U max distance is basically, we can see that on the, because U goes across and V goes vertical, we can see that this one is blatantly furthest on the right, so we can grab this number here, and then it needs to be minus, and then we should probably change these to equals as a better representation, and then we can see that this one is the one that's most on the left. So that's our two numbers for working out our U max distance. And then as we can see, this seems to step upwards, so this is our highest V number, and then it's going to be minus. And if you I mean, this one looks like it's the lower one, but if you're sort of stuck, you can just click on the Y. So that's 84778, and then this one is 86. So this one is definitively lower. So now that we've got this, we can grab our humble calculator, which is off screen, and then we're just going to pin it there. Alright, so what we need to do is we just need to grab 0.379242, and then it needs to be minus 0.327197. So that is our distance for our U, and we now just need to do the same for our V. So it's 0.150948 minus 0.084778, and then now we've got this. So if we just paste that in, so as we can see, our V is the one with the larger distance. So if we do our V, which is this, so it's that, times our texture resolution, which is 2048, and that equals 2048, this number right here. So now that we've got that, our texel density equals this number divided by real length. So if we come over to what our real length is, so we're working on the V, so it's between this point and this point. We're going to just create a bridge between them, and then we're going to scroll down to our overlay, show edge, and then look at our length. So the length is 0.448116, and then that will equal, when we find out, 0.448116, and our texel density equals this. So between our two texel densities, or should I say the texel density add-ons that we've got, this one calculates that this face is 306, and the other one that we have here, so we've got to grab the face, which reckons, so the UV width is 0.079, and then if we calculate the real length is 533, which isn't the one we've got, and it reckons it's closer to 305. So what we can do is we just now need to work out the diagonal. So judging by it, we can see that the diagonal is more than likely going to be between point 1 and 4, primarily because point 4 seems to come away to the right more so than point 2 and point 3, because they seem to be almost linear to each other, whereas that seems like it has got a bit of a stretch to go. I mean, we can sort of maybe calculate from these squares, so you've got 1, 2, 3, 4 and a bit, so maybe 1, 2, 3, 4 squares in total nearly, whereas this one spans 1, 2, 3, but it also spans almost the same, like I say, it's got the whole 1, 2, 3, 4, and then it's over here on top of, whereas this just seems to span the one sort of square rectangle here. So we're going to go between points 1 and 4. So what we've got is we've got point 1, and then we've got point 4. So point 1, we know that the coordinates for it are here, and for point 4 we know that the coordinates are here. And conveniently for us, we have already got our max distance, because 327197 is point 1 and 379242 is for point 4. But just for ease, we're just going to do our U distance equals, and then our V distance equals, and then we're just going to start and do it again without having to grab those. So point 1, we can see that our U is smaller than our U on point 4, so we're going to do 0.379242, and then it's going to be minus 0.327197. And then for our V distance, we can see that our point 1 is higher than our point 4, so we're going to start off with 0.14709, and then it's going to be minus 0.086992. And then again, if we get our calculator out, we can grab these numbers. So it's 0.379242 minus 0.327197, and then that equals the number that we had earlier. So we know that the calculator works. So now what we can do is 0.14709 and then minus 0.086992. And then that will give us this number here. So next, now what we have to do is we have to square these numbers individually. So when working out the diagonal, we basically have to, in fact if I just write it all the way down here, what we've got to do is we've got to get the two vertices, or two vertex, that are the furthest from each other, two vertex furthest, U and V. And then what we've got to do is get the distance for U and V. We've got to square them, square U and square V independently. Then what we've got to do is add, we'll start a new line, add U and V together, and then we've got to get the square root of that number. So square root of U, V. So we've got our distance, and so now we've just got to square them. So U squared equals, and then we'll have our V squared and equals. So because we've already got the number for V, we'll just do V squared first, which equals this. So we'll put that in there, and then what we can do is we can get 0.052045, and then we'll square that, and that will give us that number. Whoops. And then what we can do is U add V equals, so we've already got the U in this one, so now we can just grab this because it's a long number. So we'll just select add, paste the number, enter, and then that gives us this number here. So now we need the square root of this. So UV square root equals, and then if we press this number on the calculator here, we'll be given this number instead. So 0.079501, which is the number that we got here. So we're on the right track. So now that we've got the square root of this, what we can do now is we can times it by our texture resolution. So now we need our UV square root times 2048, which equals, and I imagine this is going to be another insane number, 2048. Not too bad. So 162, and then what we can do now is we can do our texel density, which equals our texels across divided by real length. And the real length might have changed. So our real length is going to be, if it's between points 1 and points 4, as you can see, we're now on the other side. So if we press F to make face or edge, scroll down to our overlay, and then as you can see, this is 5 or 0.5332, and 3. So we've got the number here, and then we just need to divide it by 0.533243, and then that gives us 305,336, big number, texel density equals that. So as you can see, we've got 336. So we're a little bit off compared to this one, and that could be because our precision is, no, either way, one of the takeaways that we have to make sure that we definitely remember from this is we have calculated the texel density via the edge, getting the diagonal. However, this other one that we use, I'm not massively sure how it calculates, but some are known to calculate through the UV area. So that just gives us an average for the whole face, whereas the one that we use has the longest UV edge matched to the real 3D edge to get our linear texel density. And that is why the numbers might not match. So hopefully that has taught you how to do a bit more advanced maths. I want to say it's not that hard, but it is a matter of keeping on top of all these wild numbers that you can get. Alright, so this is now going to be our follow along example. So we're going to try and not select a face that is axis aligned, so therefore we have to calculate the longest diagonal, and then through the use of that we can get our UV width, which will hopefully allow us to calculate our texel density. So to begin, we need to make a random shape. So what we can do is bring in a cube, scale it randomly. I'm just going to turn this off, then select a face, inset it, extrude it, use the spin tool, so we can do cursor to selected, and then if we do it on the X, like so, and then we'll inset again, extrude, extrude, and then we'll extrude there. Okay, so this is our shape. We're going to apply scale, we're going to make sure it's applied, and then what we can do is we can generate a subdiv, 1, 2, 3 maybe, nah, 3 is a bit much I think, and then what we can do is we can also deform it and then just throw some of these numbers around, even though it only appears to be affecting the back. Either way, we can apply that, and then what we'll do is we'll just do a smart UV project. We'll randomly throw our camera around, and then what we'll do is we'll select a random face. So something up here apparently, so let's see, or we can try again I suppose. We'll something like that, and then we'll move this, and then God, this is difficult. Why do I keep clicking off the model? So I'll just do this. Alright, hey, we got one face, excellent. So now that we've got this, we're going to zero in on it, and then scroll down, and then what we'll do is we will give it a shader, and then we'll make a 4K material. So we've been dealing with 204A, we've dealt with 1024, so let's do a 4K texture. So image, texture, new, and then we'll just call this 4K, make it a UV grid 496, and then just hide that, and then plug that in. We'll put this back to our text editor, and then what we can do is we can look at our 4K texture here, and then zoom in. Alright, so what we want to do is we want to have points 1, 2, 3, and 4. I just want to see if there's any other funky shapes going on. Maybe we should calculate this one. That one's got a definitive thing about it. So much for randomness. Anyway, so what we'll do is grab our selected face, we'll calculate the real length, and then we'll do our texture, texel density. So that says it's 247, our other one says it's 227, so relatively close. So what we've got is we need to get points 1, 2, 3, and 4. So it's between points 2 and 3. That is definitely a while away. So if we get point 2 and point 3, and then what we can do is if we just go into our edit mode and go to our vertex selection, we can grab our U and our V like so, and then for point 3 we can grab our U and our V. Whoops. Accidentally pasted that, so yeah, we need to get our U again, so U, and then we need to get our V, and there we go. So max U or U distance equals, and then our V distance equals. So our U distance is going to be this one. It's going to be 0.3 minus 0.2 because 0.3's got the bigger of the numbers. So we're just going to grab that and then do minus that, and that equals. And then for our V, it looks like our 0.2 has the higher number, so we're going to do that minus, and then minus this one. Okay, so now that we've got that, it's time to get our humble calculator. So we're just going to pin that so it doesn't disappear when we select off it. So for our U distance, we've got 0.074478 minus 0.072463. So this is our U distance. So our V distance is 0.28635 minus 0.187933, and then we get this number here. So now we need to get our U squared and our V squared. So our V squared is going to be easier because we've already got this selected, so that is our V. So now we just need to get our U, so 0.002015, and then square that, and that gives us this really small number here. Alright, so now that we've got U squared and V squared, we can now do U plus V. So that will equal the number that we've already got in, plus this one here, and then that gives us this number here. And then what we've got to do is we've got to get the square root of our UV, so UV square root, and that equals this number here. Alright, so now that we've got our UV square root, it's UV square root times our texture resolution of 4096. So what we can do is times 4096, and that gives us 403.2. So now we can paste that in. So now we need our texel density is equal to our texels across divided by real length. So our real length is between these 2 points. So with these 2 arrows selected, we select that and that. And we are now down here because this is the face we selected. So now if we scroll down to our overlay, show edge, show length, and then what we're going to do is make a face. So our length is 1.626420. So now if we do that divided by 1.626420, this is what our texel density supposedly equals. So 247. So texel density equals that pixels per meter. And if we have a gander at our texel density here, we've got 227, so we're 20 pixels off with that one. And then if we calculate it through the use of this one, calculate real length, we got 247. So we've matched this one almost on the spot. Something's gone off there, but again, depending on the add-on you use, some calculate via the diagonal length, which is what this one does, and then this one, again, I don't know too much about it, but it can be assumed it might be calculating the UV area. So yeah, basically, as long as the numbers are close enough to each other, you've got an idea of what your texel density is. So thank you for watching, and I'll see you in the next one.